Welcome to the second day of the online conference on the science of consciousness, jointly organised by the Essentia Foundation, the Sentience and Science Foundation and the Institute for Advanced Study at the University of Amsterdam. We had a very interesting first session on Tuesday, and I'm sure that today's session is going to be just as interesting. We have some very good speakers for you. Consciousness is one of the most challenging questions we face in science. The dominant model for studying it has been reductionist materialism that holds that everything in human experience, including consciousness and everything in it, subjective experience, values, meaning and love, can be explained in a bottom-up manner from underlying matter. But science is changing. Increasingly, other metaphysics are being seriously considered in trying to understand these phenomena. And that is what this conference is all about. I'm Sarah Durston. Consciousness has always been an interest of mine. It's probably the reason I became a psychologist. I'm going to be the moderator today on behalf of the three organisers. The Sentience and Science Foundation that I founded last year with my colleague and friend Leonika Terpstra. The aim of that foundation is to bring together first-hand and third-hand perspectives in exploring consciousness. The Essentia Foundation, which is equally young and aims to promote idealism as a serious metaphysics for understanding consciousness and the world. And the University of Amsterdam Institute for Advanced Study, an institute dedicated to providing a haven for researchers free from constraints of disciplinary boundaries to work collaboratively on complex scientific and societal issues. So I'm very excited to welcome today's four speakers and to introduce four more eminent speakers. All of them have very interesting and relevant things to say about consciousness. So welcome to you all. I'm going to move on to introduce our first speaker. That is Professor Dr. Erik Verlinde. Erik is a theoretical physicist and string theorist at the University of Amsterdam. He has made important contributions to theoretical physics that I do not pretend to even begin to understand, and his name has been attached to more than one formula and equation, including the Verlinde formula that he developed as a PhD student. He's best known to the general public for his theory of entropic gravity. And in this theory, gravity exists because of a difference in the concentration of information in the empty space between two masses and its surroundings. He extrapolates that to general relativity and quantum mechanics as well, and he therefore proposes that gravity is not so much a fundamental force of nature, but rather an amalgamation of other forces. That renders it an emergent phenomenon, and if this theory is correct, it will have huge consequences for how we think about the universe and its evolution. Erik and I have been working together on emergence and how the observer in emergence is part of the system, including in science. His talk today is going to be about emergence in physics and the human mind. I'm very much looking forward to hearing it. I always learn a lot from listening to Erik. Erik, floor is yours.
So indeed, I'm very pleased to be here and actually to be talking about interesting, discussions I've been having with Sarah about emergence and also the connection with consciousness. I mean, why is this relevant for theoretical physicists like me? Indeed, the ideas of emergence and why we are thinking about the laws of physics from this point of view have to do with how we are also viewing ourselves as scientists as being able to sort of understand even nature. Theoretical physics in itself is a reductionist enterprise, and I will first take that perspective, but then later on I will develop indeed ideas and actually even evidence for the fact that we should view our theories of nature as being emergent. So theoretical physics in the first instance just tries to understand what we might call the four most fundamental laws and also the most elementary building blocks of nature. And in that respect, it is reductionistic. It divides up matter into atoms and even smaller particles that make up all of the matter that we observe. And actually, scientists have been very good in discovering these laws and also finding these most fundamental forces that act between these particles. Theoretical physics has very little to say yet about the brain, although we might imagine indeed that when we understand everything that's happening at a microscopic level, that we may also eventually understand how the brain itself works. How physicists themselves don't well, entertain that thoughts. I mean, they don't consider actually the question of consciousness as a part of physics in itself. And the reason is that they're basically more focused on the questions having to do with things that have nothing to do with the human beings themselves. I mean, they take themselves out of the equation, and we look at nature as something that we can observe without the presence of an observer. Indeed, they developed in this way the standard model. Actually, it's surprisingly successful, this reductionist point of view. And the theories that have been developed have been tested at incredible accuracy. I mean, there is a system of particles that describes everything. There are forces, and there's one equation that basically contains all of this, what is necessary to sort of know about these particles. Here it's written in some shorthand notation on the mug, where you see indeed all the terms that kind of would be needed to describe the interactions between the quarks, the electrons, and all the other particles that are responsible for the forces. Again, what I said is very successful, and this is indeed seen as the most successful theory of nature, and it's reductionist in the sense that it really only describes the smallest particles. And then there is also the theory of gravity, which of course starts with Newton, and which has been generalized by Einstein to involve the curvature of space-time. Again, these equations are very successful and also seen as our best way of describing gravity at this moment. And they've been tested to all kinds of precisions. In particular, Einstein's theory has recently been confirmed quite spectacularly in its, well, predictions for the existence of black holes, for instance, and also for the existence of gravitational waves, which have been found through direct observations. So these theories are without doubt successful, and they describe very much what nature is about. And you may wonder why humans are actually so capable and so good at finding the laws of nature. This is indeed the equation that sort of controls all of these gravitational laws, just to show you that there are indeed also equations with them and not just pictures. There's another part of physics that I'd like to introduce as well, which is an older one, which is called thermodynamics. This was about just pressures and temperatures and actually basically the engines that people built in the 19th century. But eventually this was understood also in terms of what's called statistical physics. And indeed, what I will explain later, this is an example where we understand certain laws of nature as being emergent. And it's going to be a central theme actually in my presentation, that there is some way in which we can then associate a notion called entropy with this. So entropy was introduced by Boltzmann. At least he explained what it meant microscopically, and the equation is written there. It's not important what is actually there. It says something about the amount of information that is contained in the molecules that make up the gas. And this equation is actually featuring on his grave, actually. At that moment, when Boltzmann explained what thermodynamics was about in terms of molecules, not many people believed in molecules, or even the ideas that there would be atoms or things like that. There was no direct proof of the existence of these particles. And this is also what made Boltzmann's theory not generally accepted until only later, when people in the early 20th century were able to indeed provide evidence for the existence of atoms and so on. So this development was something that was not initially foreseen, and the laws of thermodynamics already existed before they were understood as being emergent. So as humans, we are looking at nature, and we basically have things we understand at large distances. I mean, that's the gravitational world, and there are things, the smaller distances, which have to do with quantum mechanics. We still have trouble combining quantum mechanics with gravity. But another thing that physicists don't do very well actually is describe the world around us at the scales of the human being. I mean, like what happens inside cells or what happens in our brain. And the reason is that physicists are very good at explaining things that can be sort of simplified. And indeed, the dynamics of the smaller particles and actually what happens at larger scales somehow appears to be more simple, obeying more simple equations than the equations that would be necessary to describe what's going on in biology or in well, molecular, well, or in our brains even. So there's some curious fact that physicists seem to sort of focus on those questions that can be described in some simple ways. And I'll actually explain why that actually is necessary, well, why actually the theories are also so successful, by thinking about how humans even are capable of deriving those laws. So you have to understand that we as humans are actually observing nature, and there are ways that we are reducing or observing these phenomena, and then deducing the theories that describe these phenomena. So this is a picture that I borrowed from the book of Roger Penrose. I actually have the book here with me. I actually wanted to use it to put on under my laptop, but anyway, the cover here is used as an illustration of how the mind works and learns about how to describe the physical world. Namely, we observe the physical world, and then we sort of enter in our mental world, and then we are developing theories that eventually end up in what would be called the Platonic world. And so these equations that I showed you, like Newton's law and everything that we have in theoretical physics, should be thought of as a Platonic realization of what happens in nature. But then we can use those descriptions to describe the physical world. And so my picture of this is sort of, well, actually goes back to what Plato already thought about. Plato had a very similar view of nature, namely he imagined in his famous elegy of the cave that human beings that don't know about the microscopic sort of Plato world actually are just seeing images of something that's underlying reality. And so that would be the person that's projecting, say, the birds on the cave, on the walls of the cave. And if humans would only be able to see the images, which are the shadows of these actual objects, they would conclude many different things about what's actually going on. So Plato imagined actually that the real description of nature is his Platonic world, which I think is indeed maybe a mistake, because even in my field, actually, many of my colleagues identify the mathematical equations very much with the real physical world as if they're the same thing. It's like we're indeed really understanding what nature is about and not taking into account the fact that we have simplified or made a model of nature in our Platonic equations. And this is actually something that I think is quite essential in how to view the theories of nature that theoretical physicists have been developing. So the various steps that you can do in between these different worlds, you can observe the physical world, and then we enter into our mental world. Then we are using these observations, and we're actually deducing the laws that are then described in terms of mathematical sort of Platonic equations. And then we use those equations to make predictions about the physical world. But in these steps, we're always kind of reducing the amount of information that we're looking at. Namely, our mind basically is capable of taking a lot of information, and in our deduction, we do an abstraction where we represent certain, well, complicated objects in idealized fashion. I mean, like a house, we can sort of represent in a very systematic way, but the real house looks very different. And if we imagine a wheel, we usually think about a perfect wheel, which is circular with the axis in its center, but there's no real wheel in the world that really looks like that. So in these deduction steps, there's also a step of reduction of information. And this is why the physical laws basically are a compression of the information that we've been observing about nature. So information is going to be a central element in what I'm going to argue for. Indeed, it's also the thing that is measured by entropy. So I'm going to actually connect this idea of information to what I call emergence, because I think once you realize that the laws of nature are obtained by compressing a large amount of information or data about the real world or the physical world, you also understand that these laws that we are obtaining should be viewed as being emergent. So what is emergence? Well, I already mentioned this idea about information and our brains using information in a certain way. Actually, recently I was asked to write about this question, is maybe our intelligence also something that is emergent? And I think it should be seen indeed as a particular property that depends on sort of a microscopic design of our brain. There's something that, namely, we are capable of that we can also do artificially, namely take a large amount of data and then compress that amount of data into what we might call useful information. On the right-hand side, you see the design of some deep neural network that has a lot of input lines. And then in every step, one just basically reduces this amount of information to eventually some useful predictions about what has been observed. I mean, if you want to see, for instance, if a picture of a cat or a photograph is a cat or a dog, then you can start with all the pixels, but eventually the prediction should be whether it's a cat or a dog. And then a neural network is capable of doing this by compressing all the information in the pixels into something that is, a statement about whether it's a cat or a dog. So in a certain way, I should think about those cat and dog features of a picture as something that is emergent. Indeed, I view or even define emergence as the following statement. I mean, here we see a photograph, indeed, where if you look microscopically, there's only pixels. But when we zoom out and we take many pixels together, we get a picture that contains mountains and trees and a lake. But also in physics, we're doing the same thing. We are describing concepts and observed phenomena at a macroscopic scale, which are derived from a microscopic scale where they have no a priori meaning. So there are basically concepts that have no microscopic reality. They can only come about by combining many, many microscopic elements together, and then they emerge as something that is bigger. It only makes sense when we look at the whole and not at the individual parts. A well-known example is these murmurations of birds or starlings here that indeed, do something together, while all the birds themselves, they are basically flying independently. That is not exactly true, of course. I mean, they do see each other, but the structures that they form can only be understood by looking at the full collection of these birds. That does not mean that we cannot describe it. And maybe it's even useful to think about a model that describes these ways that birds are flying. Namely, if you imagine that every bird sort of is flying in a certain direction, but then adjusts the velocity by viewing the neighbors. And for instance, you can make a model where you say that the bird, when its velocity is very different from its nearest neighbors, it will sort of correct its velocity and it starts moving along with its nearest neighbors. And then you add a little uncertainty in the sense that you allow it to do something a little bit random. This you can then put in a computer, and actually you'll find that these models quite well describe what's going on with these birds. You could also make the model slightly more coarse-grained by taking small groups of birds and then apply the same rule that the group of birds somehow behaves as one, where they collect and look at the information of the other birds in their neighborhood, and then they adjust their velocity together. It's this kind of step where you take one single bird and turn it into a group of birds that's also often used in physics. We call this scaling, in the sense we scale up the problem in a certain way. And it allows us to reduce the number of parameters that we're using, because if you have a large number of birds, then it's very complicated to to even keep track of all the birds individually. But groups of birds, even if that's not the entire group, is much easier. And this is actually the way that eventually you end up with models which have very few parameters, but can be quite successful in describing how these birds are behaving. As I said, the same techniques is being used even in quantum field theory. Actually, if we think about this standard model, it's based on what I would call a universal framework. By that, I mean that it can indeed be obtained by very similar steps that I just explained, where you only keep very few parameters that are describing what's happening in these experiments. And even in these experiments, people are not trying to predict how every particle is moving. The only thing that one wants to calculate are probabilities for certain particles to come out. So in the predictions that people make using these theories, one does not try to really reproduce the entire information that's contained in a single scattering event in these colliders. We simply reduce it to what we call the probabilities of a certain distribution of particles coming out. And this is also the way we can see new particles appearing by simply calculating how likely it is that a certain particle is being produced. So this standard model of elementary particle physics is also a way of compressing actually the information that we have obtained by doing many observations of these kind of collisions. And the models are quite simple and have only relatively few parameters. But I'm convinced actually that this theory, which is now considered to be one of the most fundamental theories of nature, eventually will also be understood as being emergent from an underlying theory. Let me get back to thermodynamics. Already mentioned that thermodynamics is maybe one of the first theories in physics that was understood as being emergent. And here we can even quite explicitly explain what we mean by emergent. Namely, here we have properties of a gas of particles, with many particles that are like the temperature or the pressure, which, if you think about it microscopically, are just average quantities that can be defined only by averaging over many particles. An individual particle does not have a temperature, and an individual particle does not have a pressure. These notions are only meaningful when we talk about many particles moving together. And a central element in these laws of thermodynamics is also the notion of entropy. This is exactly what Boltzmann realized, and he defined indeed entropy as the number of possibilities that microscopic molecules have to be moving around in this container, for instance. And it's, in that sense, it's sort of like an amount of information, microscopic information, that's required to describe all the motion of these particles. And in a way, you can think about entropy as just counting the number of bits that is necessary to describe what is going on at the microscopic level. This microscopic information, however, is not being kept because when we treat the gas simply as something that has a temperature and a pressure, we're averaging over all those microscopic possibilities. But we have to keep track of how much information then is being thrown away. So this coarse graining is quite an important step in deriving these universal laws of thermodynamics. Now, I'm also going to talk back to gravity, because in gravity, we also have very fundamental laws. And you may wonder whether these laws are emergent as well. And I'm going to be indeed arguing they are. And there's a lot of evidence for this that comes from studying the gravitational laws, and actually in circumstances where we, can basically test the limits of the theory. I already mentioned that Einstein's theory of general relativity predicts the existence of black holes. And there's now lots of evidence for black holes. People have even made pictures of black holes, and we have studied their behavior when they start merging together and studied the gravitational waves. But as theorists, we're also thinking about more theoretical questions, more kind of thought experiments, what will happen near black holes. So what is a black hole? A black hole is actually an object that is so dense that no light can even escape. And a black hole has then therefore a kind of imaginary boundary or a sphere around it, that if you would pass through that sphere, I mean, you cannot escape, because light can not even escape, and nothing can go faster than light. We call this boundary the horizon, and it has a certain size that depends on the amount of matter, the amount of mass that is collapsed to form the black hole. So black holes, they can form when a star is burning out of fuel, and then if there's no fuel anymore, then the gravity will basically take hold of all the matter and make it sort of disappear or collapse onto a point, basically. And this is exactly what Hawking and Penrose both showed, is that matter always will be contracting, and then there will be a horizon forming. Eventually the matter forms ends up in the origin, and it forms a singularity in space-time. And it's for this work actually that Penrose also received the Nobel Prize a few years ago. But what was more important actually is that they discovered that the laws that describe these black holes, they have properties that look very much like that of thermodynamics. I mentioned the property of the horizon, and actually that horizon is a measure of the amount of information that has disappeared behind the horizon, and actually can be thought of as, again, a kind of entropy. And what they showed, and this is sort of the beginning of an important development in theoretical physics, is that the gravitational equations actually near black holes are really equivalent, and they look exactly the same as the laws of thermodynamics. And so here I have just for your illustration, I mean, I'm not going to explain the details of these equations. On the left-hand side, these are the equations that we know very well from thermodynamics. They're actually developed already in the 19th century. On the right-hand side, we see equations that are describing how black holes behave when matter is being added and how the horizon sizes change. For instance, you see that horizon size can only increase, and which is also a property that entropy has in time, that entropy can only increase. And also the sizes of these black hole horizons can increase. And it's precisely because we believe that the laws of gravitation and those of thermodynamics look the same, that we also are currently understanding more about where these laws of gravitation come from. The laws of thermodynamics can be derived from statistical physics, and there's a similar kind of microscopic explanation of the laws of gravitation, except now we are not dealing with microscopic building blocks, which are atoms. We have to talk about quantum properties of the space-time and many things that I don't have time to explain, having to do with what's called quantum entanglement. I just want to give you the general idea that indeed, just like we can derive thermodynamics by averaging over molecules, there's some way in which the microscopic description of space-time, when we average over its properties, give rise to the laws of gravitation. We don't have a proof of the existence of these microscopic building blocks of space-time, but just like in Boltzmann's time, we didn't have a proof of atoms. Maybe at some day, by looking at observations, we can eventually find also proof for these emergent laws of gravitation. Now, I'm wondering how I'm doing with time. I think I'm almost at the end, actually. Indeed, this is sort of my summary, is actually that I have argued for you that by thinking about how we obtain our laws of nature by reducing basically, or taking the information that we've observed and putting it into a framework that we call a theory, is actually a step that is like a compression of information, and that in that step that we necessarily are going to end up with emergent theories that eventually need to be sort of derived from what actually is underlying. And this is in general how I think about the laws of nature that we have currently, is that we should look for the underlying principles and building blocks that eventually will tell us how these theories that we currently are having are emerging. And I believe actually this will eventually also give a different explanation of certain phenomena that we currently don't fully understand, like what's happening in galaxies. In galaxies, we don't understand exactly how gravity is working, because we seem to have more gravity than we can explain in basis of the matter that we see. And having a better understanding of what gravity is, of how it emerges, I believe will also indeed change or allow us to maybe solve those problems. Similar questions that we have about the early times in the universe. I mean, in particular, what happened near the Big Bang, or what really made the universe appear or maybe emerge, are questions that may be very different when we think about gravity in this emergent framework. So this is what I want to finish with, is just indeed the idea that thinking about how we develop theories of theoretical physics actually also allows you to think differently about what the meaning is of these equations. And my conclusion is that every equation that we have sort of obtained should be seen as being emergent in some form from a microscopic underlying picture. Thank you for this.
Thank you, Erik. That was very interesting indeed. Very inspiring. Yes, the viewers at home, anybody who has questions to Erik or any of our speakers later should feel free to enter your questions in the chat box, and then we can pose them to the speakers. Also, the speakers themselves, if you have questions that you would like to pose to Erik, please let me know. Erik, I have a question, if I may start off, which is if we go back to the model that's on the Penrose book cover, the mental world, the physical world, and the Platonic world, where in that model would you place consciousness?
I think you're still seeing my slides, or not?
No, we can see you. We don't.
You can't see it anymore. Anyway, that's a good question. I mean, I think there's, of course, the mental world where we are sort of having most of our experiences, but we can only define ourselves or even be aware of our consciousness in relation with the physical world. Yeah. So I think that in the interaction between our inner brain and the environment, we sort of see this, and we also have an image of ourselves in our Platonic world. So I feel that consciousness is something that is only appearing when all these exchanges are happening between the physical world, the mental world, and the Platonic world. And I think the actual sense of self, or where your images of yourself, there's some way you have this also in your Platonic frame. There's some sense of I that you have sort of simplified to your inner self that I think is part of what consciousness is about. And so I feel that this is kind of in the middle of this whole picture. It's not something that can be placed entirely in your mental world, because I think if you have a brain by itself that has all the neurons in every interaction, every neural interaction that we know about, I don't think that brain will develop consciousness if it doesn't interact with the other worlds, the actual physical world. And it would not be able to do those deduction steps and have some Platonic simplification of that world. So I think it's part of the entire story.
Okay, thank you. We have a question from Bernardo, I think. Your definition of emergence seems consistent with what David Chalmers calls weak emergence, but sometimes in your talk you talked about it as if it was something ontically new, as in strong emergence. Could you clarify?
Well, strong emergence, I think, is probably what is meant there is that there's no real explanation of it, or there's a really fully new phenomena that can never be sort of deduced. I would think that there are examples of strong emergence, but strong emergence also is maybe then a statement in principle. I mean, I think there's always a principle maybe that, so if you ask me, is emergence really something that's totally different from reductionism? I don't think so. I mean, there's some way in which they can go together, in the sense that emergence may also mean that there's a very complicated way in which something can be derived from the underlying description. So I think that then still the notion of emergence is quite useful, because it actually means that there's never going to be a final sort of fundamental description, that everything that you have eventually will have something that's still underlying it.